We are going to be taking a look today at hypothesis testing once again. So continuing on our discussion of Chapter 5 in our Studenmund textbook. But unlike the T-statistic, which tests a hypothesis regarding a single coefficient, we're going to expand that out to looking at how to test a null hypothesis that involves multiple coefficients, or joint significance testing, which is going to take us from the T-statistic to the F-statistic. So typically, right, when we're estimating a model, we're going to have more than one x variable predicting our y variable, so a multiple regression scenario. And it's basically every time it's going to be really useful to be able to know whether or not, as a group, our coefficients are significant, right? Or as a group, our variables are adding meaningful explanatory power to our model. So we're going to be conducting this so-called joint significance approach to hypothesis testing. And a great place to start with is what we'll kind of call our default or our Goodnessoffit version of this joint significance test, is when you have a null that all of your coefficients are equal to 0 versus an alternative that at least one coefficient is significant. Right? So this is basically your question, is my model doing anything at all? Is the combination of variables that I've decided on, do they have any explanatory power over y? Or kind of, are we just wasting our time? Or is y explained by other things or entirely random? Right? So we're obviously going to need a different approach from the T-statistic approach that we discussed previously. And the logic of this F-statistic, F-testing methodology is what I like to think of as a little competition between two different models, our so-called restricted and our unrestricted models. And it's the definition of these two models that's really going to drive the intuition and the procedure that we're going to follow for the rest of this discussion. So, how do we compare the performance of two different models? Well, we already know how to do that, right? We have a variety of things we could look at. We could look at the R-squared, the adjusted R-squared, or we could go right down to the kind of the bare bones of it and look at the sum of squared residuals. Right? The better a model performs, the more explanatory power it has, the smaller will be the sum of squared residuals, the RSS. So when we talk about a restricted model, the restriction of interest is that in the null hypothesis, right? Which coefficients are we setting to 0 in the null, right? Again, with the T-statistic, it was always just a single coefficient. Now with this joint significance testing, we're putting multiple coefficients in the null, setting them equal to 0. And what the restricted model does is just says, well, how would that model perform if that null was true? Let's set those coefficients to 0, effectively removing the variables in question, and then calculate the sum of squares and compare that to the unrestricted model that includes all of the variables that we're interested in. Okay, so when we think of the unrestricted model, that's essentially our structural equation. It's the model that we're trying to estimate, and then the restricted model is a subset of that. So some good news, the information that we're going to need, the calculations that we're going to need to make, is all material that we're familiar with, basically from our previous discussion of the R-squared and the adjusted R-squared. Right? So the primary ingredient is that measure of accuracy, that sum of squared residuals, the RSS. And now we're just saying, well, it's going to come from two different sources, the restricted and the unrestricted. So RSSR and RSSU, respectively. And it's also going to be useful for us to go back and think about those other key ingredients to the R-squared, the total sum of squares, the TSS, and the explained sum of squares, the ESS. And we'll only look at those from the unrestricted model. Okay, so the idea here again, it's a competition. It's a horse race between RSSR and RSSU. And we want to figure out if imposing the restriction meaningfully changes the explanatory power of the model. So this is where we get into going from a measure of accuracy to a test statistic, right? So it's always going to be the case, right, that the restricted model performs worse than the unrestricted, right? There's less information, there's fewer variables there. Whether or not that difference is statistically significant is going to require us to have a known distribution and a set of critical values that we can compare that distance to. So the calculation, it all starts in that same place. Let me bring up my pen here. It all revolves around this comparison, but again, to turn that into a test statistic, we're going to standardize that by the number of restrictions. We'll talk about that, but that's basically the number of coefficients that we're setting to 0, and standardize that whole thing by our sigma hat squared, the estimated variance of the error term, the EI or the UI, depending on your notational preference. Right? But that's all kind of the mathematical requirement for this, that raw difference, to follow a known distribution. So if you were hoping for a formula to memorize, here it is, right? So the F-Statistic formula all revolves around this here, right? So the RSSR minus RSSU. So when we impose the restrictions, we set those coefficients to 0, how much do our residuals rise? How much does the performance of our model suffer? So that's the difference in the performance of the models divided by the number of restrictions. So M represents how many coefficients are set to 0. And then all of that is divided by RSSU over N minus K minus 1, which you may recognize as our sigma hat squared. Right? So in words, right, the difference in the sum of the squares relative to the number of the x variables in the null, all divided by the estimated variance of the error term, the sigma hat squared. Okay, and then this note here is just a reminder that in this initial case that we're considering, where we set all of our coefficients equal to 0, then k, the total number of coefficients in the model, is the same as m, the coefficient set to 0. We're taking everything out to make this restricted versus unrestricted comparison. That's not always going to be the case, but in this scenario it is. So now this is the part where we have to talk about why are we doing all this? Why are we dividing by the number of restrictions in the sigma hat squared? Again, there's a lot of math behind this that we're not going to get into. The key element that we want to talk about here is that it all requires that classical regression assumption number 7 to be true, that the error terms are normally distributed, right? Because if that's true, then the sum of the squared errors will follow a chi-square distribution, and it can be shown that the ratio of 2 chi-square distributions follows an F distribution. And what that buys us, right, is a known distribution. It buys us the calculation of the probability of seeing a certain value. In other words, it gives us critical values. We can now say whether or not our F calculation is large enough such that we can reject that null, right? So without that, we're back to just saying, oh, one model is different from another, but we can't say if that difference is just because of random chance or it's a structural difference indicating whether or not those coefficients really are 0. So one thing to note, that this F ratio, unlike the T statistic, the F statistic is always going to be positive, right? The difference in those sum of squares, the restricted versus the unrestricted, is always going to be a positive number. The restricted model is always going to perform worse. It's always going to have a larger residual sum of squares. So we don't have to worry, are we in the left-hand tail, the right-hand tail? It is a one-tail test, a two-tail test. It's always going to be a one-tail test, and it's always going to be on the right-hand side. So we're going to have a distribution that's heavily skewed to the right, and we're only going to have that one critical value. And it'll look something like this, right? So the 0 point here, right, that's basically the null, right? That if the null is literally true, if those coefficients are all equal to 0, then it makes no difference. If we put the variables in, we take the variables out, and the F ratio is going to go to 0. And what we want to know is if our positive F statistic is large enough such that we can conclude that it's not just random chance, right? That the true value is 0 and we just happen to get one out here. Well, that's going to depend on the critical value, right? So for example, if our number of restrictions, the numerator degrees of freedom is 3, the n minus k minus 1, the denominator degrees of freedom is 60, this would be what our distribution looks like, and our 5% significance critical value would be 2.76. That'll give us 5% area in the tail. And that would give us our rejection versus non-rejection regions. Obviously, where that critical value is going to be and the exact shape of that distribution is going to depend on those degrees of freedom. So just another quick word about, again, kind of the intuition, the logic of the test. It's the same story that we told with the t-test, right? So remember, with the t-test, we had that distribution centered at 0, right? And then we looked at the critical values in the tail, right? That's kind of the picture that we looked at. And the idea is that we put this distribution based on the null hypothesis. This is the state of the world if the null was true. And then we look for enough evidence to say whether or not we can reject that null and say, well, this really isn't where the distribution lies. The same thing with the F-test, right? That if the null is true, the coefficients are 0, and the F-stat equals 0. In order to reject that null, we have to be able to say, well, it's less than 10%, 5%, 1% probability that we would get the value that we see if that null was true, right? So what is the probability of seeing the strongly positive F statistic that we calculate, for example, just by chance, just by random chance across repeated samples, if the null was true? If that's highly unlikely, we say we reject the null and conclude our coefficients are not 0. So again, the mechanics look a little bit different. The calculation certainly is different, but the underlying story should be familiar. And not to beat this up too much, but the real foundation of the story, again, only makes sense if we keep in mind this hypothetical idea, this theoretical idea of repeated samples, right? That when we run a regression, we're just taking one set of random errors from the population and estimating our coefficients. And I think we should be comfortable with that idea that across repeated samples, we have random errors, therefore we have random coefficients. Well, it's not much of a leap to say the sum of squared residuals, the RSS, are also random across samples. Every time we grab a separate set of Y observations, we run a separate regression, we'll get a different RSS. So it's the same idea. Are we seeing this big difference in residual sum of squares just because of random chance from our one sample, or is it a structural feature of the data generation process? And then, I already mentioned this, but can't stress it enough, this whole process only works, right, if we have a normally distributed random error term. And we're pretty much relying on assumption at this point. But just remember that that assumption number 7 does play a big role. We didn't need it to show we have an unbiased OLS coefficient. We didn't need it to show the derivation of the variance, but we do need it for both the t-statistic and the F-statistic. So essentially what it comes down to is a recipe, right? What are the steps of conducting an F-statistic? It's always going to look something like this, right? We're going to start by, I guess, before this, we need to have an idea of what the null hypothesis is. Once we figure that out, and again, in our example, it's always setting all of the coefficients equal to 0 at this point. And then we basically run the two equations. We run the model in its unrestricted form with all of the variables included. Then we take all those variables out, we rerun the equation, and we calculate the RSS in both scenarios. We plug those numbers into our F-statistic formula with the correct degrees of freedom. Then we calculate, or I should say we look up the appropriate critical value based on our significance level, based on our degrees of freedom. And then we make the comparison. And if our calculated F-statistic surpasses the critical value, we can reject the null. We have found joint significance in our coefficients. Right? So if our calculated F-stat greater than the critical value, we're way into the right-hand tail, we say it's highly unlikely, right, that the true values of these coefficients are 0, and we would get this result. So we conclude at least one of the coefficients that we've included is not 0, or taken as a group, they are jointly significant. And from our, again, kind of default Goodnessoffit point of view here, I'm being somewhat facetious here, this is something to celebrate, right? It's basically saying, aha, the variables that I've gathered here in my model lets me predict my y variable with more accuracy than I could come up with if I only used an intercept, a constant, right? So it's a pretty low bar to get past, but definitely information that we're going to need. Which brings us to the other case. If your calculated F-statistic is not that large, the gap between the restricted and the unrestricted sum of squares is pretty small, and your F-stat doesn't surpass the critical value, we don't reject the null. We could say we could have just got this result by random chance. It's not that big of a difference. And now none of your coefficients are significantly different from 0. You're basically not outperforming a model with no x variables at all. And it basically says your variation in your y variable is either entirely random or, again, explained by other factors. And I probably should not have said this, right? We don't want to make a value judgment. If you're, from the point of view of trying to construct a model that gives you accurate forecasts, accurate predictions, this is not good, right? Your choice of x variables are not doing the job. But without a normative statement, it basically just says, okay, your y variable isn't a function of the x variables that you have chosen. So let's take another quick look here at this specific Goodnessoffit or default F-statistic case. This case where the number of restrictions is exactly equal to the total number of coefficients. Because it turns out we can get a nice little mathematical simplification that will make it easier to calculate and also easier to interpret this F-statistic result. Because think about what it means to have a restricted model when m is equal to k. That whatever variables we initially had here, we take them all out in the restricted model. We're setting all of our coefficients to 0, all of those slope coefficients to 0. So we're effectively estimating now a restricted model with only a constant and an error term. Not a lot going on there, right? Well, if we did this in OLS, the fitted value, right, the prediction, the B0 hat, the only thing on the right-hand side here after estimation, is going to be the sample mean, right? So the sample mean, our y bar, is going to be playing the role of our predicted value, our y hat. So if we plug that in, right, our residual term for a given observation is going to be the difference between y and its predicted value, y and y hat, which is y minus y bar. So that gives us this nifty little result. The sum of the squared residuals will be the sum of the squared deviations of y from its mean, which is our total sum of squares. Again, this only works because of the lack of any x variables on the right-hand side here. So stick with me just for another second here. What does that mean? If we go back to our formula, right, where we had this RSS minus RSS, but we plug in TSS, right, for the restricted residual sum of squares, then this should look familiar, right? The difference between total variation and the variation we can't explain is the explained sum of squares, right? So we can plug in the ESS into the numerator term. And again, this gives us two different things. Basically, it says we can calculate this whole ratio now without ever referring to the restricted model. We can just get the explained sum of squares and the residual sum of squares from the unrestricted model to make this calculation. So that'll save us some time. And the other nice thing is this is now starting to look something like an R squared, right? So think about what happens when the performance of our model increases. The ESS goes up, the RSS goes down, and the R squared goes up. We're explaining a greater percentage of the variation. Well, as that happens, the F-statistic is going to go up as well. So they're going to be moving in concert, right? And we can see that a lot easier here with this ratio than we could with that original formula. So I do want you to kind of think about this. It's a question that I often ask, say in a quiz or a midterm. Compare and contrast this F statistic with our R squared, right? And it's kind of a Venn diagram, right? There's definitely some overlap between them. They're both measuring how well our model fits the data, right? The explanatory power of our model. But they also both have unique aspects, right? So the R squared has that real convenient interpretation, the percentage of variation that we can explain. But what it doesn't have is critical values. It doesn't have a distribution to go along with it. We can never say, my R squared is high enough so I can conclude that my model is significant. That's what the F-stat gives us. So we can't interpret the number of this F-stat as saying that it's a percentage variation or anything like that, but we can compare it to critical values and draw a conclusion about significance, which we can't do with the R squared. So again, all of that was true from the beginning, but it's easier to see, I think, with this version of the formula. Okay, one last thing before we actually take a look at some numbers. Also a big time saver, of course, is the p-value, right? So just like with the t-test and with any other test statistic, we can cut to the chase. We can get to the end result real quickly if we can calculate and interpret appropriately the probability or the p-value associated with a given test. So just as before, that p-value is going to be giving us the highest level of significance at which we can reject the null. So the bigger the F-stat is, the farther into the tail we are, the smaller the p-value will be. And if, for example, that p-value drops below 1%, 0.01, well, that tells us we can reject the null with at least 1% significance, at least 99% confidence. And at that same level, again, just for example, if we see a p-value greater than 0.01, well, we can't reject at 1%. But think about it, again, as that kind of graduated scale, right? When that p-value is above 10%, we do not reject the null. When it drops below 10%, but it's above 5%, we can reject at 10% significance, but not quite 5%. It drops below 5, but still greater than 1, we say we can reject at 5%, but not 1. And then finally, if it drops below 0.01, we can reject at that strongest level of confidence, 1% significance. Okay? So once we get kind of some examples under our belt and we start to use this in Stata all the time, that's the number that we'll go to, right? Once we know the p-value, we can tell the rest of the story without doing much additional work. But we got to earn that, right? By doing it the hard way first. So one more time, let's go back, all the way back to week 1. Man, that seems like a long time ago, where we had that little 9 observation example consumption function data set, where we had our Y household consumption, for example, our X household income, and remember we showed piece by piece how to get the B0 hat, the B1 hat, the Y hat, and the residual, and that gave us these numbers. We had a sum of squared residuals, the RSS, of 190,000. Remember, we used that to calculate the R-squared, and likewise we had an explained sum of squares of 27.5 million, roughly. Well, we now know that those are key ingredients to calculating the F-statistic as well, so let's go ahead and see what that would look like. We've got ESS over M, which in this case is just 1. We've got one coefficient, and we set it equal to 0 in the null, over RSS over N minus K minus 1, and we plug that into our calculator, and we get a whopping 1016.36. What does that mean? Well, it's way above the critical value, which is about 5.5. So you flip to the back of your textbook, you'll see several F critical tables. We'll take a look at those in a second. And that means we can very strongly reject the null that one coefficient was 0. Again, it's a trivial exercise in this case, but that's the mechanics of doing the calculation. What is not a trivial exercise is being able to read that F critical table, right? So remember, with the T table, each column that we saw gave a different level of significance. Here, because there are 2 degrees of freedom that we need to know, the numerator and the denominator, we have a whole table that is 1 level of significance, and each column gives us a different numerator degree of freedom, and each row is a different denominator degree of freedom. Right? So it takes a little bit of practice to know what we're looking at here, but we have M equal to 1, so we're in this first column, N minus K minus 1 of 7, so we're in this 7th row. So that's where that critical value of 5.59 came from. And just looking at the values here, again, with the T distribution, if you know nothing else, you know a T-stat of above 2 is probably significant, right? That's kind of a rule of thumb. Obviously, you need to know the degrees of freedom to know exactly what you're looking at. But here, a value of about 3.5 is around the significant level for reasonable levels of sample size down here. So when you see a number like 1,000 or like 50, you're saying, okay, this is going to be significant, right? But we still need to know how to look up the exact critical value. And of course, Stata does all of this for us, right? So we haven't talked about it up till now, but every time we've asked Stata to estimate a regression model, it's done this exact calculation for us. We've just overlooked it. So this F-statistic that Stata calculates for us is always testing the null that all of our coefficients are 0. Again, in this case, we only have one coefficient. but we should be able to show exactly where this calculation came from, and it came from over here, right? The model sum of squares, that is our explained sum of squares. Residual sum of squares, that's the RSS, and our degrees of freedom here are 1 and 7 respectively, and that's where that value came from. So you should be able to use these numbers to reverse engineer where this value came from. And then we look down below and we see that probability greater than F. That's the p-value associated with this F statistic. 0 out to 4 decimal points, well below 0.01, highly, highly significant. We can strongly reject the null, again, that our coefficient is 0. And again, we didn't need to do that here because we only have one coefficient, so its t-stat is highly significant. So its f-stat is going to be significant as well. Examples that we'll see later will have multiple coefficients. But just to see piece by piece where it came from, I think it's worth going back to look at that original data example. And we'll go ahead and ignore this. So this is how to get the same output from R or RStudio. I'm not going to require you to use that, but if you want to get into R and RStudio, let me know. And I may be giving you an extra credit assignment that will ask you to do that later on. But we don't need that for now. But the picture is useful. So again, now we've got some numbers to plug in here. So this would be our critical value, the 5.59, and the 5% rejection region, right? To the right of that, well, we calculated our F, right, of 1,000. So we're way into the tail. We're way out here, well into that rejection region. Again, a strongly significant coefficient. Okay, so that is the, again, so-called default or Goodnessoffit application of the F statistic. Well, there's another application that's going to be also extremely useful, and this we'll just call kind of the general or the walled test application, where we want to test joint significance of multiple coefficients, but we might not want to apply that to all of the coefficients on our model at once, where we want to apply it to just a subset of our independent variables. Okay. So in a generic scenario, if we have y as a function of 3 variables, x1, x2, and x3, there may be scenarios where we want to look at, say, just x2 and x3. We want to know if those two variables taken as a group give us meaningful additional explanatory power. In other words, can we reject the null that those two coefficients, b2 and b3, are 0? As opposed to the alternative where at least one of them is non-zero, that taken together, our model is better, right, with those variables included. They are jointly significant if we can reject that null. So the good news is, once you've decided on which variables it makes sense to group together and what that null hypothesis is going to be, the procedure is exactly what we've discussed, right? The calculation, the formula is exactly the same. And it all comes down to running that comparison, right? The restricted versus the unrestricted model. And the difference between them, same as before, is going to be what are the coefficients set to 0 in the null. So if this is the original model, we want to test the joint significance of x2 and x3. We take those variables out and then estimate the same equation, the same y variable. And x1, note, never moves. It stays there the whole time. And it's only x2 and x3 that are included or excluded as we go from the restricted to the unrestricted model. But the calculation is exactly the same. So once you have that formula memorized, you can always use it. We can't use that little shortcut, right? There's no ESS substitution we can make. We've got to run the restricted model. That'll give us the RSSR. Run the unrestricted model. That'll give us the RSSU. M, in this case, is equal to 2. 2 coefficients set to 0 in the null. And then the same RSSU, and then the n minus k minus 1 from our sample size. Note here that, again, k is equal to 3, because in the unrestricted model there are 1, 2, 3 variables, but m is only 2 because only 2 of them are set to 0. So that's by far the most common kind of calculation mistake that is made, is messing up the m and the k in the formula, right? Well, I guess the most common is forgetting the formula, but once you have that down, make sure you know what numbers go where, right? So m, the number of restrictions, k, the total number of variables. So once we do that, right, we run the model, we make our calculation, and if we see a large enough F-statistic, it surpasses the critical value, this gap is big enough that we conclude adding those variables is helpful. It meaningfully reduces that residual sum of squares. On the other hand, a small F-statistic, taking those variables out, putting them back in, doesn't make a big difference. They're not significant. Do not reject the null. So let's take a look at an actual example here, and it's the same one we always look at. We've got a wage determination model, and say we have education, total work experience, and then tenure on the right-hand side. And just keep in mind that your tenure is how many years you've been at your current position, as opposed to experience is total number of years in the labor force, right? And it might make sense because these are both kind of generally getting at job experience as determining your wage, that these might be two variables that could be grouped together in a null. We want to know, okay, if you take those together, do they significantly add to our explanatory power? But this model here is what we'll call the unrestricted model, right? Wage as a function of all 3 variables. And once we know that we're going to be running a joint significance test, we're going to estimate this model, and we're going to take this number, right? That's the residual sum of squares. That'll be the RSSU, right? Because this is from the model with all of our variables. So we're no longer looking at this guy, right? This F-stat of 76, that's testing the joint significance of all 3 variables. We just want to look at these 2. So we have to do this on our own, right? Stata only knows to test all 3, in this case, all k of our variables. We want to just look at that subset of m of 2, right? So what do? We rerun the model, but without the 2 variables in question. We take experience and tenure out, imposing the restriction in the null, setting b2 and b3 equal to 0, and we now have our comparison, the RSSR, the restricted sum of squares. And we take a look at the number of observations. We're going to need that n, right, to go into our degrees of freedom portion of the calculation. But now we have all the pieces of the puzzle. So we've got RSSR minus RSSU over m of 2, all divided by RSSU over n minus k minus 1. Boop, 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 boop. That's the sound my calculator makes. And we get a number equal to 53. Now, we already saw, right, being somewhat familiar with the F table, 53 is going to be pretty big. It's going to be significant, but we want to make sure, let's get the appropriate critical value. So we're going to go all the way down to the bottom of the that F critical table, and this is, again, an example of a 5% critical table, and we want to find the right spot, right? So M is 2. The N minus K minus 1, right, we had 526 observations, so it's going to be here down beyond that 120 value. So we can go ahead and use the bottom row, and it's going to give us a value of 3.0. So obviously, 53 is bigger than 3.0, so we can strongly reject the null. So taken together, experience and tenure are jointly significant. That would be the conclusion. So you should be comfortable walking through something like that. So every time after we cover this, the following quiz, the following exam will have exactly this setup, right? You'll be given this Stata output from an unrestricted model right next to Stata output from a restricted model. You've got to calculate the appropriate F statistic and draw a conclusion using the F critical table. Okay, so be able to work through some examples of that, and you'll be in good shape. In real life, right, when you're walking through problem sets or doing your project, Stata will do all of this for us. Okay, so there is a post-estimation command, conveniently called the test command, that will apply this f-test to the null that we specify. Again, Stata can't do this automatically. We have to tell it which coefficients we want to set to 0. So it would look simply like this: test, and then you list out the variables, the variable names whose coefficients are set to 0 in the null, and Stata does the calculation for us, gives us the F statistic, and even more conveniently gives us the p-value. So here, that p-value well below 0.01, we can strongly reject the null that those coefficients are 0. So as soon as you see that, say, aha, these are jointly significant. They should stay in the model, right? Taken together, they add significant explanatory power. And yes, it's that easy. So when you're asked to do a joint significance test, you run the unrestricted model, you use the test command. Okay. So in the slides, there's a couple other issues that are brought up. I'm not going to test you on that, so I'm posting up the non-narrated slides. You can take a look at that. But as long as you can apply that F statistic to the default, right, explain how that Stata calculation comes up for the joint significance of all the coefficients, that's number one. Number two, be able to apply it to a subset of coefficients, comparing the RSS of the restricted versus the unrestricted, and you will be in great shape. So shoot me an email. Let me know if you have any questions on this material or as you're working through the problem set, and we'll see you, well, I won't actually see you, but I'll be posting up slides again on Monday when we get into Chapter 6, and we'll see how this goes. Thank you very much.